All right, and with that, we're going to start and we're going to cover sections 7.5, 6, and 7. 7.5 is called rationalizing radicals. Okay, it's basically a form of division. All right, rationalizing is kind of a way of saying clearing of the radicals. So when you have division of radicals, is it generally considered not simplified or unsimplified if you still have a radical in the denominator? So to clear that, we're going to do a step called rationalizing. Now this goes kind of similar to the simplifying fractions, which you've already done. So you can change a fraction by multiplying the same number to the top and the bottom. You're essentially multiplying by a form of 1, and that doesn't cancel it, or that doesn't change it. It just makes it look different. So to clear a radical, if you take a square root times itself, okay, square root of 2 times square root of 2 is the square root of 4. And of course, we know that the square root of 4 is 2. So if you take a square root times itself, it becomes itself with no radical anymore. Okay, so that's a way we can clear radicals. If you can take a radical times itself. So again, root of 2 times root of 2 is the root of 4. Obviously, root of 4 is 2. No more radicals. Now, again, if you're going to multiply something to the bottom, you've got to multiply that same thing to the top. And if we multiply 1 times the square root of 2, we get 1 square roots of 2, which is the square root of 2. So this is considered simplified or rationalized. Now they can do a couple of different things. If they give you something that looks like this, square root of 3/5, an easy thing to do is just to rewrite that as the square root of 3 over the square root of 5. And again, to get rid of a radical on the bottom, we're essentially going to take it times itself. And whatever you multiply to the bottom, you also have to multiply to the top. Square root of 5 times the square root of 5 is 5, no longer a radical. Root of 3 times the root of 5 is the root of 15. So again, that is considered simplified or rationalized. Now, another thing to pay attention to, if you have a halfway decent calculator, like I showed you last time, when you're just dealing with numbers, okay, if you have a sophisticated calculator, it can do that for you. For example, if I type in the square root of 3 over 5 and I hit equals, my calculator says the square root of 15 over 5, which is what we had here. So if you're dealing with just numbers, no variables, no letters, double check your calculator might be able to do that for you. That'll save you some work, which is kind of nice. Okay, if not, that's when you got to go through the steps and or the process to get there. Now, if they give you letters and variables, then it's obviously a completely different animal, because you can't type in square roots of X into your calculator, and that's where we would have to go through the steps. But if it's just numbers, okay, you might have a calculator that'll do that for you. Anyway, if you're dealing with variables and numbers, one thing I'm going to say, you're going to hear me say this multiple times, but I'll talk about outside numbers and inside numbers. Okay, that's just an easy way for me to refer to what is inside of the radical as opposed to what is outside of the radical. Okay, this is like saying 8 times the square root of 2. Okay, and in math we have like terms, and anyway, you can't combine outsides and insides. Anyway, if we want to rationalize this, we want to get rid of the square root of X. So again, we're going to multiply the square root times itself. Square root of X times the square root of X is just X. No longer a radical. And now if we multiply 8 times the square root of 2 times the square root of X, we can multiply the radical. So here, like square root of 3, sorry, times square root of 5, that was the square root of 15. Radicals you can multiply together. That one that was outside, multiplying the square root of 2, we didn't combine those, okay? That one stayed outside. So this 8 outside of the roots of 2, okay, this is like saying 8 times the square root of 2 times the square root of x. So we would get 8 square roots of 2x all over x. And that's considered rationalized. Now, also be aware, 9 times out of 10, most of the time when you're being asked to rationalize, they are implying for you to rationalize the denominator. It is possible for them to ask you to rationalize, not 4, let's do 14. Okay, they could ask you to rationalize the numerator. Okay, if they're asking you to rationalize the numerator, they just want to get rid of the radicals on the top of the fraction. They're saying radicals are perfectly fine on the bottom. We want to get rid of the radicals on the top. Most of the time, we're trying to get the radicals off of the denominator. The directions will probably say to rationalize the denominator. But most of the time, that's what's implied. To be considered simplified, you want to get the radicals off of the bottom. But occasionally in your homework, they're going to ask you to do the top. So it's the same game. We just want to change the numerator. We want to get rid of the radicals on the top. So we're going to multiply by the square root of 14. Square root of 14 times square root of 14 is just 14, no longer a radical. Square root of 2 times the square root of 14 is the square root of 28. Now, I haven't touched on this before because none of these others required simplifying, but that square root of 28, we're not done, okay? One of the previous sections, we talked about simplifying radicals. So if I go and kind of revisit, so the square root of 28, 28 is 2 times 14, which is 2 times 7. With a square root, we're looking for pairs. And if you have that pair of numbers, it goes outside, and then whatever's left over stays in. So the square root of 28 can be rewritten as 2 square roots of 7. Now, another thing to pay attention to is with fractions, if you can divide something out of both the numerator and the denominator, we need to be able to simplify those. 14 and 2 are both divisible by 2. 14 divided by 2 is 7. 2 divided by 2 is 1. So we have 7 over 1 square roots of 7. Now the 1 in front, you don't necessarily have to write 1 square root of 7 is just the square root of 7. But if they ask you to rationalize the numerator, you got to get the radicals off of the top. In this case, that would be considered rationalized. Now, the trickiest problems of these are ones where they have addition and subtraction in them. For example, 3 divided by 1 plus the square root of 2. Once you have addition and subtraction, that adds some difficulty to this. All right. To get rid of the radical, you can't just multiply by the square root of 2, because if we distribute, that'll get rid of the radical there, but then you're going to multiply it by 1 and you're going to get another square root of 2. So that's not really helpful. So when you have addition and subtraction, to get rid of the radicals, what you multiply by is this thing called the conjugate. Now, it's not important what it's called, but that is what it's called. And it's essentially this same thing, but with a different symbol. So instead of 1 plus the square root of 2, what we're going to multiply by is 1 minus the square root of 2. And again, you multiply same thing, top and bottom. That way we don't change our fraction. In doing so, when you multiply by the conjugate, Okay, if we FOIL this out, multiply those first pieces, 1 times 1 is 1. 1 times the negative square root of 2 is the negative square root of 2. Positive square root of 2 times 1 is the positive square root of 2. And positive square roots of 2 times negative square roots of 2 is negative 2. Because again, root of 2 times the root of 2 is the root of 4. Root of 4 is 2. Anyway, positive times a negative is a negative. Now, if we combine our like terms, the negative square root of 2 plus the positive square root of 2, those two things cancel each other out to equal 0. That's the benefit of multiplying by that conjugate. Those middle terms cancel each other out, getting rid of our radicals. And again, combine like terms, 1 plus negative 2, that's just a negative 1. So when you have a plus or a minus with your radical, you got to multiply by what's called the conjugate. Now, the numerator, we still have to multiply, so we distribute. 3 times 1 is 3. 3 times the negative square root of 2 is negative 3 square roots of 2, which looks like we should be able to do something. But again, these are not like terms. This is just a 3. This is 3 roots of 2. They're not the same. We can't combine them. So I would consider this simplified. Now, my math lab doesn't want you leaving a 1 on the bottom of your fraction. So if we divide both of these things by negative 1, we actually get negative 3 plus 3 roots of 2. Ultimately, I'm okay with either. My math lab is definitely going to prefer this version of the answer. And all I did was divide everything by negative 1. 3 divided by negative 1 is negative 3. Negative 3 roots of 2 divided by negative 1 is a positive 3 roots of 2. Now, because these are the trickiest ones, I will do a couple more examples like that. Okay, so again, a similar example. If they give you something like this, and again, the directions will typically say something like rationalize the denominator. Okay, again, they're wanting to get rid of the radicals on the bottom. Again, when you have a plus and a minus, what you've got to multiply by is the exact same thing, just with a different symbol. Instead of plus here, we did minus. Instead of minus here, we're going to do the plus. Okay. Again, we distribute square root of x times the square root of x. That's just x. Square root of x times the square root of y is the square root of xy. Square root of x times the negative square root of y is the negative root of xy. And negative root y times positive is negative y. Negative times a positive is a negative. Root of y times itself is just y. And again, those middle terms cancel each other out, leaving me with just x minus y. Multiplying the top, distribute, square root of x times square root of x is x. Square root of x times square root of y is the root of xy. Root of y times x is also the root of xy. Root of y times root of y is just y. Now, these two middle terms don't cancel each other out because they're both positive, but we can combine that into 2 square roots of x, y. So just remember, when they give you a plus or a minus with the radicals, to get rid of it, you got to multiply by what's called the conjugate. Okay, same radicals and variables, just a different symbol. Now, they may still ask for you to rationalize the numerator with one of these. So same game. Again, the only way you can get rid of radicals of the plus and minus is to multiply by that conjugate. We multiply 3 times 3, that's a 9. Positive 3 roots of 5, negative 3 roots of 5, that's going to cancel. Negative roots of 5 times the root of 5 is going to be just a negative 5. 8 times 3 is 24. 8 times the root of 5 is 8 roots of 5. 9 minus 5 is 4. And again, normally we would be done. And with here, we were. Now, again, when dealing with fractions, if your outside numbers are all divisible by the same thing, we've got to factor or divide that out. So we got to simplify our fraction. So 4 and 24 and 8 are all divisible by 4. So if we divide, 4 divided by 4 is 1. 24 divided by 4 is 6. 8 divided by 4 is 2. So again, we can simplify if we can divide all of these numbers by the same thing, which those are all divisible by 4. So that gives me a simplified rationalized numerator of our problem. So 7.5 is going to start off fairly simple. Okay, they're going to give you just some plain kind of fractions to rationalize. They're going to throw in some variables. As long as it's just numbers, you might have a calculator that does that for you. Then it's going to get more complicated. They're going to throw in stuff with the pluses and the minuses. So make sure you're paying attention. Now, the one last thing they may do is they may give you a non-square root. So for example, if they ask me to rationalize 3 over the cubed root of 6, okay, to get rid of it, you're no longer having to multiply by itself. Remember, with a cubed root, you're trying to figure out what number times itself 3 times, okay? So to clear this of the radical, remember, we need 3 6s. Right now we've got 1, we need 2 more. 6 times 6 is 36. So we get 3 cubed roots of 36 over cubed root of 36 times the, or sorry, cubed root of 6 times the cubed root of 36 is the cubed root of 216, which the cubed root of 216 is 6 with no radicals anymore. So again, to clear a cubed root, you need 3 of some number inside. So I needed 2 more 6s to get rid of the cube root. Anyway, and that's over 3 cubed roots of 36. And again, if your outside numbers are all divisible by the same thing, we got to divide. 3 divided by, or 3 and 6 are both divisible by 3. So we end up with 1 cubed roots of 36 over 2, or just the cubed root of 36 over 2. So if they happen to throw in a non-square root, you're not again taking it times itself, but you need again 3 of those numbers. Okay, now something to pay attention to, and it's kind of nice here, is to get rid of the cube root. Again, I need 3 of some number. Now I could multiply by 2 more 4s, so I could multiply this by the cube root of 16 to clear it. However, remember 4 is 2 times 2. And if I need 3 of a kind, I really only need another 2. So then I can have 3 2. So I can save myself a little bit of work by multiplying by a 2. That gives me the cube root of 8, which is just 2 with no radicals. So if you have a number that you can break down, okay, you might only need one more thing. Cube root of 5 times the cube root of 2 is the cube root of 10, which doesn't break down. So we would just end up with the cube root of 10 over 2. And that's basically 7/5. They're going to ask you to rationalize denominators. They'll give you some non-square roots, mostly regular fractions. Then they'll throw some in addition problems where you've got to do that conjugate. All right, we're going to switch to 7/6, which of the lessons, to me, this is all what algebra is about. This is solving radical equations. I like solving because we're going to get pretty little answers and we can check our work instead of getting all these ugly radicals in all these different, configurations. We're going to get stuff we can actually solve. Okay. So they're going to give us something like the square root of 3x plus 2 equals 5. All right, to solve a radical equation, the first thing you want to do is you want to isolate the radical. So anything going on outside of this radical, you want to get rid of it. If you're adding something, you need to subtract it or add the opposite. If you're multiplying something, you need to divide it to get rid of it, okay? You need to get this radical piece by itself. In this case, we've already got that. The square root of 3x plus 2 equals 5. This square root of 3x plus 2 is by itself. Nothing's going on the outside. That part's done. Then we use exponents to clear the radicals. So again, to undo a square root, we are going to square it. And again, what you do to one side of the equation, you got to do to the other. So squaring a square root gives us what is inside, not a radical anymore. We square 5, 5 squared is 25. And now we have a regular linear equation, one variable that we can solve for. So if we subtract 2 from both sides, 3x equals 23. Divide by 3, x is 23/3. Now, you are also going to need to check your solutions. Not every single time, and I'll tell you when it's extremely necessary and you have to, but it's a good idea to check your problems anyway. But there are going to be some problems, and I'm going to show you where you're going to do all of the math right, but some of those answers don't work. Again, you get an extraneous solution. In this case, if we check our solution, the square root of 3 times 23/3 plus 2 should equal 5. 3 times 23/3 is 23. 23 plus 2 is 25, and the square root of 25 is 5. That checks out. This is a good solution. Most of the time, that's going to be the case. Now, they could give you something that looks like this. Okay, that's supposed to be equals. So 2 minus the cube root of x plus 1 equals 3. Again, the steps, we want to isolate this radical piece. So anything going on outside, we need to get rid of it. To get rid of a positive 2, we need to subtract. 3 minus 2 is 1. Okay, a negative, you can't distribute into the radical. So to get rid of a multiplier out in front, we got to divide. So we're going to divide by -1. So the cube root of x plus 1 equals -1. Once you get the radical by itself, we're going to use exponents to get rid of it. Now, squaring got rid of a square root. So to get rid of a cubed root, we are going to cube it. Cubing a cubed root is just whatever was inside. -1 cubed. -1 times -1 times -1 is -1. Solve for x. Subtract 1 from both sides. X equals -2. And again, we can check our solution. -2 plus 1 is -1. The cube root of -1 is -1. And 2 minus a -1 does equal 3. This is a good solution. All right. When we might potentially not get a valid solution, or you might have to check, is when you have x's on more than one side. For example, all right, so 3. Oh, sorry, x. It's supposed to be an x. I was like, that's still going to give us a solution. Anyway, that's supposed to be an x. X minus the square root of 3 minus 2x equals -6. Okay, so again, to solve, we got to isolate the radical. That means we got to move this over. So the opposite of a positive x is a negative x. Again, to get rid of this negative, we're going to divide everything by a -1. Now, to get rid of the square root, we square. Remember, to square the quantity, you don't just square the individual numbers. Squaring a square root, that goes away. Now remember, squaring a quantity, x plus 6 quantity squared, is like saying x plus 6 times itself, which if we FOIL, we get x squared plus 6x plus 6x plus 36. Which if you'll remember, now we have a quadratic. To solve a quadratic, it's not about just solving like we would a linear equation where you just try to isolate the variable. Okay, when you have a quadratic, you've got to get everything on one side. And then we've got to solve by factoring or using the quadratic formula. I'm going to factor. So x squared is x times x. And then I'm specifically looking for two numbers that multiply to get 33 that are also going to add to get 14. That would be 3 and 11. So then if I set my factors equal to 0, x could equal -3. Set my factors equal to 0, x could equal -11. Now, I did all of the math right. Okay, if you go back and look, all of the steps, everything is just fine. However, whenever I go to check my solutions, one or both of these solutions might not work. So we gotta check and see. So I'm going to take my original problem, okay, of x minus the square root of 3 minus 2x equals -6. And I'm going to plug in my -3. And we'll just see what happens here. So 2 times -3 is -6. 3 minus a -6 is 9. Square root of 9 is 3. -3 minus 3 is -6. Okay, that checked out. -3 in this case is a perfectly valid solution. It worked out. Okay, we're going to try the same thing with the -11. So x minus the square root of 3 minus 2 times -11 should also equal -6. If I plug that -11 in, -2 times -11 is positive 22. 22 plus 3 is 25. Square root of 25 is 5. And the square root, or sorry, -11 minus 5 is -16, which clearly does not equal -6. -11 is an invalid extraneous solution. So when you have multiple x's and we go to solve, okay, you have to check your answers because maybe they both work, maybe they both don't. In this case, only one of my solutions was a valid solution. When I did the math right, this one should work, but whenever I go to check it, it's clearly not a valid solution. So you do need to check your solutions. It is entirely possible to get something that doesn't work. All right. The last type of equation they may give you that we have to kind of deal with is if they have radicals on both sides. Now, when you have two different radicals, and the steps are to isolate the radical, in this case, they are both by themselves. So to get rid of my cube roots, I can again cube both sides, and essentially that just gives me whatever was inside of the radicals. And now this is just a linear problem we can solve. Subtract 2x from both sides. Subtract 7 from both sides. And x should equal -12. Again, with x's on both sides, we do need to check our solution. So if we plug in -12, three times -12 is -36. -36 plus 7 is a -29. 2 times -12 is -24. -24 minus 5 is also -29. The cube root of -29 is going to equal the cube root of -29. That one again checks out. That is a valid solution. So 7-6, in my mind, is the most straightforward section within this whole dang unit. 7-1 was nice, dealing with perfect squares or perfect radicals. This one is probably the next nicest, where we get to do some solving. You get to actually figure out what x is. It's going to be a pretty little whole number, and you can always check your solutions. I like being able to check and make sure I got something right. All right, last but not least, 7-7. The last thing we're going to talk about tonight, the last thing we're going to talk about in chapter 7 is imaginary/complex numbers. Okay, so if you'll excuse me for a second, I just got to go back and kind of revisit some stuff that we've already talked about. So we've already talked about simplifying radicals. For example, if I needed to simplify the square root of 24, remember the idea of breaking 24 down. 24 is 2 times 12, which is 2 times 6, which is 2 times 3. Okay, remember with the square root, we're looking for pairs. That pair of 2's comes out. Anything left over stays inside. So that reduces to 2 square roots of 6. Okay, another way to look at this is 24 is 4 times 6. The square root of 4 is 2. So again, that's just another way to write it. Now, also, previously, when you were given the square root of some negative number, again, the square root is asking for what number times itself is equal to whatever's inside. There are no real numbers that multiply to get a -4. It's either 2 times 2, which is +4, or -2 times -2, which is also +4. So there were no real solutions to this. Somebody decided that we needed to have solutions to the square roots of negative. So they invented this thing called an imaginary number. Pardon me. They said I, a lowercase I, it's actually kind of a scripty looking I. Okay, a lowercase I is going to be equal to the square root of -1. What this allows is now, even though this is not a real solution, we can simplify this down to an imaginary solution. For example, the square root of -4 can be rewritten as the square root of 4 times the square root of -1. So the square root of 4 is 2, and that square root of -1 is I. So now we can simplify negative square roots. That will yield an imaginary solution. So the first part of 7-7, they're going to ask you to do just that. They're going to tell you to simplify some negative square roots. The easiest way to do this is, okay, square root of 5 doesn't break down, but that negative inside of a square root, again, makes this an imaginary solution. So the square root of -5 is actually I roots of 5. Now, some people write the I after the square root of 5, which is perfectly fine. However, you got to be careful, because if it looks like you put the square root of 5 I like that, the I cannot be in the radical. The square root of I is not the same as I being on the outside. So if you put your I at the end, make sure it is clearly outside of the radical. Inside of the radical is bad. This is not the same thing, not equivalent. I'm okay with either of those. They both basically mean the same thing. I prefer the I to be in front, but it's neither here nor there. Okay, we're told to simplify 3 square roots of -50. Okay, square root of 50 breaks into 5 and 10. 10 breaks into 5 and 2. So again, that pair of 5's comes outside with the 3 that's already there. We've got a 3 outside. That 5 goes outside. That poor little leftover 2 stays inside. And again, the square root of a negative makes this imaginary. So what we end up with is 15I square roots of 2, or 15 roots of 2I. And again, I'm okay with either of those. Now, not so much for this section, but in conjunction with the first section, remember, cube roots of a negative are not imaginary. Only square roots of a negative yield an imaginary solution. Cube roots can be negative. Okay, a cube root is asking what number times itself 3 times is -8, and a negative times a negative times a negative is a negative. So the cube root of -8 is just -2. That is not imaginary. Remember, imaginary numbers are only when you have the square root of a negative. The square root of a negative yields an imaginary solution. So be aware of that. Now, with imaginary numbers, you also get these things called complex numbers, and a complex number just combines an imaginary portion with a real portion. For example, they may ask you to add 3 plus 2i and 2 plus 5i. This is considered a complex number. We have got a real portion and an imaginary portion. The good news is math plays really nicely and follows a lot of the same rules. And if we're going to add complex numbers, remember the only thing you can add in math is like terms. So 3 plus 2i plus 2 plus 5i, we can add our real portions. 3 plus 2 is 5, and 2 i's plus 5 i's would be 7i. So if they ask you to add complex numbers, you simply add like terms. Kind of along the same lines, if they ask you to subtract, subtraction is just adding the opposite. So if they're asking you to subtract, remember to distribute that. That changes your signs. So 2 plus I minus -2 plus 4i is 2 plus I plus 2 minus 4i. Anyway, change it to addition, then you can combine your like terms. 2 plus 2 is 4. And then I plus a -4i. Remember, if you don't see a number in front, it's like there's a 1 there. So 1i plus -4i is a -3i. So if they ask you to add imaginary numbers, you can only combine like terms. Not to be confused with multiplying complex numbers. Now, when multiplying, again, follows the same rules as real numbers. When you multiply two quantities, you have to distribute. So if we multiply 3 times 5, that's 15. 3 times 2i is 6i. And 2i times 5 is 10i. And 2i times 2i is 4i squared. Now, this I squared is important. Okay. This is going to do something that kind of seems counterintuitive, but remember, I is equivalent to the square root of -1. That's what the I stands for. The imaginary number is the square root of -1. If we square I, then we're squaring the square root of -1. We just talked about this in the last section. Remember, squaring a square root cancels it. So I squared is -1. It is no longer an imaginary number. When you square I, it just takes your number and makes it a negative. So I squared is really a -1. 4 times -1 is a -4. So again, if I combine like terms, 15 plus -4 is 11. And then 6i plus 10i is 16i. So if we multiply these two complex numbers together, we get 11 plus 16i. And along those same lines, if they tell you to square a complex number, again, remember, you can't just distribute your exponent. That's not how that works. Squaring a complex number means essentially multiplying it times itself. So if we take 3 plus 5i times 3 plus 5i, okay, we multiply. 3 times 3 is 9. 3 times 5i is 15i. 5i times 3 is also 15i. And then 5i times 5i is 25i squared. And again, I squared is -1. So that just takes my 25 and makes it a -25. Combine like terms, 9 minus 25 is -16. 15i plus 15i is 30i. So they're going to ask you to simplify square roots of negatives, make them imaginary. They're going to ask you to add complex numbers. They're going to ask you to multiply complex numbers. The last thing they're going to ask you to do, and this kind of goes back to 7.5, is they're going to ask you to divide. So 5 plus 6i divided by 3i. Okay, with imaginary numbers. Imaginary numbers are like radicals. We can't have radicals on the bottom. So when you're dividing imaginary numbers, that's very similar to 7.5. And what we have to do is we have to rationalize. Again, to get rid of I, we got to multiply it by itself, because that's going to make this. Okay, we distribute here, we get 5i plus 6i squared over 3i times I is 3i squared. And again, remember that I squared just simply becomes a -1. So what we have is 5i minus 6 over -3. And again, now we can rewrite this. So this is a -5/3 I, and then -6 divided by -3 is a +2. Now, it doesn't matter what order you do this in. I don't mind having the imaginary number first. Some people don't like that. They're going to put the real number first. But that's neither here nor there. But when dividing, you got to get rid of the radical on the bottom. You basically have to rationalize, very similar to 7.5. Again, if they give you a plus or a minus, the only way to get rid of your radicals or your imaginary numbers when there's a plus and a minus is, again, to multiply by that conjugate. Same thing, different sign. Whatever you multiply to the bottom, you also have to multiply to the top. So if we do this on the bottom, 1 times 1 is 1. 1 times 2i is 2i. -2i times 1 is a -2i. -2i times +2i is a -4i squared. Which, if we combine like terms, again, that +2i and that -2i add to get 0. I squared is -1. -4 times -1 is just a +4. 1 plus 4 gives me a 5 on the bottom. No longer imaginary. That's what I was looking for. Okay, same game on the top. Distribute. 3 times 1 is 3. 3 times 2i is 6i. 2i times 1 is 2i. 2i times 2i is a positive 4i squared. Again, I squared makes that a -1, so that's a -4. -4 and 3 is -1. 6i plus 2i is 8i, which if we divide, we get -1/5 plus 8/5 I. So when dividing imaginary numbers, you got to clear the imaginaries off of the bottom. If it's just an imaginary number, you can multiply it by I to make that a real number. If you have a plus and a minus, you got to multiply by the conjugate. And we got done relatively quickly, but that finishes off chapter 7. That's the last thing that I'm going to cover tonight. That finishes off chapter 7 again. So next week we just have Monday and Tuesday. Campuses are closed down for Wednesday, Thursday, Friday, so we will not meet next week. I will go ahead and push out the chapter 7 test, so you could do it Monday or Tuesday next week if you're just in a hurry to get it done. If not, you have the entire next week after Thanksgiving to get the chapter test done. Again, the chapter 7 tests are going to be just like all of the other. They're pencil and paper. You have to set up your appointment and get it done at your testing site, just like we've done with all the previous tests. So nothing new, but you've basically got 2 weeks to make sure you have all of your homework done. The homework is in my math lab. Make sure you do that. And then again, I'm going to stick around. I'll be here till 8:15. So if you have questions, ask. But if not, you are free to go. That's the last thing I'm going to cover. So remember, next week, no class, not meeting. Enjoy your Thanksgiving. The following week, you guys need to test over chapter 7, set up your appointment, test at your proctored site. And then the week after Thanksgiving, we finish up class. That'll be the last thing I'll teach. I'll teach the 3 sections in chapter 8. And then all we have left is the final. So as the semester is rapidly winding down, make sure you're taking care of business and getting the grade that you want to get. If you have any questions, you can ask them. Otherwise, I'll see you guys in 2 weeks.
So will there be a test over chapter 8 or no?
Won't be a test
Okay.
over chapter 8. The test is just over. So there's a test over chapter